showing up, and good morning. So, I would like to talk about Morse theory in the context of a theory in differential topology. So, the references for this talk are Milner's book, and for the most part is basically Milner's book, Morse theory, and Odin and Damian book on Morse theory and Floer homology. So, in fact, the goal of this talk is sort of to motivate at the end how one would think of constructing Floer homology. Okay, but so let me write Morse theory. So, as a theory in differential topology, I'm going to say in differential topology. So, our setting is as follows: we have M is a smooth and dimensional closed manifold. Uh, okay, n is finite, obviously, but towards the end, I will try to sort of convince you that most of the constructions that we've done, not most, but yeah, sort of the big picture that we've done can be done for infinite dimensional manifolds and not necessarily closed with boundaries and so on. And the second object that I need is a smooth real valued function. So from this, we instantly, or we, yeah, directly have a picture in the cotangent bundle presenting the zero section of M. That's all in the cotangent bundle. And let me say you have the section of F. Okay. So let me define these. It's more of terminology, but they are definitions. Um, So basically, critical points, or I will say P is a critical point of F. That's basically a point of intersection with the zero section in the cotangent bundle. So if and only if the F intersection the zero section at, let's say, P is non-empty. Okay, so this is basically it's actually the same as saying that the differential is zero, but that's the graphical description. Now we say my critical point is non-degenerate. And that's when basically the section of F intersects transversely the zero section at V. For instance, this is a non-degenerate, 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 and this is basically degenerate. Okay, by transversal, the tangent space of the cotangent bundle basically can be splitted as direct sum of the tangent space of df and that of zero section. Okay, so now we are in good shape to say that f is a Morse function if and only if all critical points of f are non-degenerate. Okay, so for instance, this example is actually an example of a non-Morse function. Okay, so let me now give you a couple of remarks, especially about non-degenerate, not equivalence constructions of non-degeneracy. So Locally, let's say 1, um, on M, i.e. if I give myself local coordinates on M, non-degeneracy is equivalent to saying that our favorite matrix, the Hessian matrix of F, second derivative, all at P, is a non-singular matrix. That is, its determinant is non-zero. And a coordinate-free description of non-degeneracy is saying that I require the Hessian of F, say xp, yp, x, y of F, all at P, um, to be um, uh, symmetric by linear form on the tangent space. Okay, so basically all of these characterizations of non-degeneracy are the same. You can think of it as graphically, where you're looking for points of the intersection of sections of F with the zero section to be transversal, or you can do it sort of algebraically by computing sort of a Hessian matrix, which only makes sense at critical points, and study if it's determined as non-zero or not, or study the quadratic form or symmetric bilinear form on TPM. So, okay, let me give you an example, and I guess this example we will stick to for the rest of the talk. Um, okay, so everyone's favorite example in Morse theory is actually the torus. Okay, so here I consider a vertically standing torus, and my Morse function is, I would say it is a height function. Okay, so you basically take a vertically standing torus and you project it onto the z-axis. Okay, so that's actually an example of a Morse function, and to see the critical points, you just imagine the tangent space, you project onto the z-axis, and if you got a point, then that's a critical point. Otherwise, you would get the whole real line, and that's not it's not a critical point. Okay. Now, let me set notation at this stage. Um, uh, so for A, real number, we define this A, the set of all x's where f is less than or equal to A. That's basically the sublevel set of, uh, of f. So for instance, if let's say this is A, then M sub A, it would be this okay. Now, okay, so we have our torus and we have this nice Morse function, and certain level sets will give me, or sub-level sets give me a smooth manifold, for instance, this case. But for instance, let me consider now taking the pre-image of this critical point, alpha. So F inverse of alpha it would actually be a wedge of two circles. So we can clearly see that it's not a manifold. So basically, what's happening here? We know that at the point that's not a critical point, the pre-image or this sublevel set, I'm having a manifold, but at critical points, the topology gets fuzzy. Basically, I can have critical points where their pre-images is actually not a manifold. So let us try to organize our ideas. So I would say by this remark. So now, so if A is not a critical value of f, then we know by the implicit function theorem that first thing we know that f inverse of A is an n minus 1 smooth manifold. Second is that the sublevel set is an n manifold with boundary the pre-image of A. Okay, now I have to show, or I will try to convince you. Okay, so for now, we have that we formalize sort of that the sub-level sets at a non-critical value is actually a manifold. Okay, but now I have to actually try to convince you that if you take another sub-level set where you compare two sub-level sets where in between you don't have critical points, then they are diffeomorphic. So by this, this means that if you want to study the handle body of a smooth manifold, or if you want to study how the topology of these sub-level sets they are changing, you only just focus on the critical points of the Morse functions, which are actually finite. So in this case, in the case of the torus, there's only 4 points where the topology of sub-level sets are changing. So, okay, to reduce this or to try to just consider the critical points, I have to show the following proposition. So basically, if f has no critical values in this interval AB and R, um, so then MA is basically diffeomorphic to MB. Okay, proof. Um, okay, that's definitely a sketch, but I will try to convince you first. Um, okay, so I'm considering two sublevel sets, MA and MB, where there's no critical points between them. So first thing to do is that we pick a metric G on M, and then we consider um, uh, basically the gradient of F. Okay, and that's by definition, that's basically the G dual um, uh, of the differential. So gradient F, okay, F, Y, let's say since I mentioned, okay. In fact, when you are dealing with closed manifolds, everything is embedded in Rn, so you can actually just work with the Euclidean metric, but then you have to pick your Morse function. Nice, but yes, let me not consider this. Okay, and then you um, take the flow along um, the negative gradient of f. So these arrows, basically, they represent the gradient vector field of f, and then you flow MB basically along negative the gradient of f. Okay, so here there is an important point is that so you don't have critical values. Okay, there's no critical values in AB. Then basically this vector field is non-zero, so I'll say one can show that the norm is non-zero. So this means here between the blue region and red region of these circles, my vector field is actually non-zero, and then I can in fact find the desired diffeomorphism. And there's okay, I'll say that's a sketch, but there's one last point that one has to um, uh, take care of is basically normalization. You have to actually show that MB will end in MA, and yeah, okay. So, so now what is the picture for now? We have that um, the topology of sublevel sets are only changing at critical points, and if you want to compare two sublevel sets where there is no critical points between them, they are diffeomorphic. So as I said earlier, basically now I just consider 4 points, for instance, in the torus, or finitely many points when you are considering a closed manifold, in order to study the topology or the handle body, as we will say. Okay, so okay, long story short, um, you add handles upon passing through a critical point. Okay, correspondingly, with the index of a critical point. Okay, so there is this notion that I have to define, and I guess this one that you may have guessed already. So I'll start with the easiest, which is talking about index, because we've already set up everything. So basically, we define the index. Okay, let me go back. We have, from now on, f is always a Morse function. So we have a critical point of my Morse function f. We say an index of f at p is basically the same as the index of the Hessian. Okay, which as a reminder is this. Okay, which basically means, okay, so let us recall this matrix or this form, as we said, it is a symmetric bilinear form. So you can diagonalize it by -1 and 1. So we basically the number of minus eigenvalues to be um, precise, negative eigenvalues. Okay, so that's sort of the algebraic, how you would calculate the index. The geometric motivation of index, it's more of, it's like you count the numbers, the number of directions in your tangent space where f is decreasing. Okay. Um, so let me just write it like this: count directions, number of directions in TPM where f is decreasing. Okay. So let me clarify this by giving an example in dimension 2, which is basically the only dimension that I will work with. Um, so this critical point has index 0. Obviously, okay, if you believe the geometric characterization, at this point you have no direction where f is decreasing. Here, my Morse function is actually the height function where, yes. Um, now, okay, so a maximum be something like this. Index 2, you have two directions on the tangent space where my function is decreasing, and you have sort of saddle point, saddle, which is of index 1, where it is increasing in one direction and decreasing in the other. So, okay, now we have the other part that I should define, which are handles. So, recall my manifold is n-dimensional. So the n-dimensional k handle. Okay, so n basically stands for the dimension of the manifold itself. K stands basically for the index of the critical point that I'm passing through. It's basically given by h and k. Let me write it as dk cross dn minus k. Um, so you are basically adding a thickened cell to your manifold. By thickened, if you notice that the dimension of the handle is actually n-dimensional. It is the same as the dimension of the manifold itself. But all you are doing actually is reconstructing the cellular homology or CW complex or CW structure of your manifold using this Morse function, but in a way that you use handles so that you will preserve the smooth structure. Okay, so this is a really important idea, and it's actually the heart of Morse theory, is that you recover the smooth structure on M, not just the topological one. That's why you use handles rather than cells. So let me just give you how handles look in dimension 2. So a zero handle is actually just a disk with sort of a mark or a point. Um, of index 1, it's basically a square, but I like to think of it as a belt. And you actually topologically get the same thing, which is you also add a disk um, when you pass through an index to critical point in a two-dimensional smooth manifold. Okay, so how do you glue these handles? Basically, you glue along the boundary, and that's a particular boundary called a boundary of my handle. Okay, so let me define what do I mean by that. A boundary. We take boundary of this and we cross it by the boundary by the disk. Okay, so let me just illustrate. This is the boundary here. Okay, so notice I didn't take this part. Okay, this is a boundary. It's in fact that's how you do it so that you preserve the smooth structure on your manifold. Okay, so now doing this inductively, namely starting by phi, and then okay, you have a critical point, you give it a handle body, and then you glue a handle body, um, and gluing, let's say along, let's say H, you take an embedding into where n is an n-dimensional manifold with boundary. So now I'm just trying to illustrate what happens in the middle of this inductive process. So you get n prime, um, you define it to be n, glue along h and k. And you repeat as much as you have critical points correspondingly to the index, so on and so forth. Is there any questions at the moment? No? Okay. So let's do an example. Um, so I will start, okay, so let's consider um, the two-sphere with the height function. Okay, once again, by the height function, I mean it's a two-sphere embedded in R3, and we're just projecting onto the z-axis. Okay, so this guy looks like this. You have here a critical point, and you have here a critical point. Let's say this is P, and this is Q. Okay, so we start by the empty set, and then we pass by our first critical point, which is P, and the index of P is what? Just to see if you're following.
Is it -2?
Mm,
Or is
it
it
is.
2? I can't remember
It's,
now.
okay, yeah, no worries. So it's actually a minimum. So it has index 0. Okay, so index 0. So I have to add. No. Okay, let me try. So I give myself this guy or a D2, but sort of curved at its center. And then when I pass through Q, we know that's of index 2. So I should give myself, I should glue this guy along the red region. So I would recover S2. So that's basically an easy example. You only have uh, two critical points and they are maximums. And in fact, that's actually a theorem, um, an interesting theorem in Morse theory where, okay, so given a manifold and you are able to find a Morse function where it only has two critical points, then it is necessarily this manifold is homeomorphic, not diffeomorphic, to a sphere. So yeah, that's actually something nice to know. And in fact, it is used by Milner when he proved the exotic seven spheres to actually, yes, prove they are homeomorphic to the same thing, but they don't have the same smooth structure. Okay, now let's sort of consider vertically standing torus. Basically, it is the favorite example in Morse theory because you have all possible indices. You have a max, min, and the saddle point. And because it's easy. Standing 2 torus with the Morse function, the height function. Okay, so let me draw it. That's A, that's B, C, and this is D. Okay, so we do inductively. We start from the empty set. We pass through our first critical point, which has index 0. So I give myself something like that. And now we pass through critical point B where it has index 1. So I give myself a belt. Okay. Now I can proceed in 2 ways. I can just follow Morse theory or sort of this algorithm by adding another handle corresponding to C, or I can just um, basically, uh, how would I say this? Um, if you imagine, okay, along this red belt, the blue circle, it's getting larger. So sort of, okay, let me, let me do the Morse theoretic algorithm. Now I pass through another critical point C of index 1. So I should give myself another belt. Okay. Uh, Now I claim that this is easy to see, hard to draw. Um, uh, yes. So I claim that if you have this sort of hemisphere, you add 2 belts. Okay, you lower one, you higher the other. Okay, you can have them to share the same endpoints. That doesn't really matter. And then you just move this black region along the red belt and the blue belt, and you will get something like that. Is it obvious? Or it's not? Okay. Um, okay, so let me go a bit. Okay, so upon passing through point B, you add sort of a red belt, right? Okay. Who can do you who agrees on that? Okay, and then you do the same thing by adding sort of it's hard to draw it, a belt, and then you push the whatever it's called, the boundary of or the black region along the blue one. Is it now easier to visualize?
This one makes more sense because I think what you did on your on the left at the bottom is
Mhm.
that you put this belt, but then you only glue the same boundary region
Yes.
of but in fact you're not, right? Because you're putting this belt that connects the two different boundary components.
Okay. Is it a question or clarification?
Both perhaps.
Uh,
I know.
okay, let us just. I guess this is easier to imagine. You just okay, lower this belt, and you uh, well, what's the right verb of it? Move, like push the black region along the um, uh, red belt. Okay, so actually, Morse theory, this is the nice part of Morse theory, where you have these type of pictures to solve. Yeah. Anyway, so we are actually doing well. Okay, so let me just okay. So now, lastly, okay, so we still have one more step. We are at this level, and I should add another. Okay, upon passing through D, which has index 2. Um, so basically, this guy, I just close it like this. I put, uh, yeah, sort of disk. Okay.
Could I ask a question?
Yes, sure.
With this handle body construction, are you really reconstructing the smooth manifold or just the underlying topological space?
No, it is the actual smooth manifold.
The actual smooth manifold? Okay,
Yes,
thanks.
and that's actually my. I guess I mentioned it, but okay, now that's actually my remark. So basically, uh, so basically, from a smooth function, one can get a CW structure on M, and hence you can recover cellular homology easily. Um, okay, and so this construction is actually called the handle body decomposition of M. And yeah, in fact, it's a theorem that the handle body is actually diffeomorphic to the smooth manifold itself.
Sorry, can
Okay.
I ask one more question?
Yes, sure.
So earlier you said if you only have two critical points, you're homeomorphic to a sphere, but not diffeomorphic to the sphere.
Yes.
Um, could you say, like, it doesn't really make sense in relation to this diffeomorphism thing that you're talking about here?
Doesn't really make sense about the.
Yeah, what am I trying to ask? I'm trying to say, like, if it seems like if you only have the two critical points, you want to like reconstruct the sphere using this handle body decomposition,
Mhm.
but you're saying that that recovers the smooth structure as well. So why for the sphere do you not get the diffeomorphism, but only the homeomorphism? Do you know?
Because you actually have spheres that are not diffeomorphic, but homeomorphic. Like,
Okay.
I'm not seeing your.
Yeah. Okay. Never mind then. It's yeah. Maybe I'm not asking a good question.
Basically, if you are okay, you have a manifold and you were able to find a Morse function that only have two critical points, then automatically you can say that this manifold is homeomorphic to a sphere.
Yeah. Okay. Thanks.
Um, okay, now let me okay, talk about Morse homology. And here things would be more sloppy. So okay, so here is where I would like to talk about the like sort of a modern aspect or the Floer theoretic way, but it is definitely a sloppy one, and nothing is rigorous will be said at this point. So first we define our Morse complex. MC star F. To be basically a graded complex, say graded, namely you have something MCK of F, where MCK of F is basically generated by critical points of index K with the Z2 coefficients. Okay, so here I actually don't want to talk about orientations, so I just consider Z2 coefficients. And okay, so MCK is just Z2 of let's say critical point A direct sum Z2 critical point B, blah blah, so that A and B and all the points have the same index K. And so this is my complex. Okay, now before I define the differential, I have to talk about something. So let us consider two critical points of F, P, and Q. And I will assume that the index of F at P is greater than or equal to the index of F at Q plus 1. Okay. Okay. Do I have to read chat now? I can talk more about this if you want at the end of the talk. Okay, so now some new mathematical language. So we consider the moduli space, let's say MPQ, curly M, of flow lines along minus the gradient of F from P to Q. Okay, so basically this actually means you take MPQ and you define minus or flow lines along this from P to Q modulo reparameterization. So let's see this construction by a simple example. So we consider S1, and we're taking its height function or projection on the y-axis. Okay. So then I have two critical points. Let me stick to notation P and Q. So basically, my moduli space of flow lines would be just two elements. I have this direction and this, say S1 and S2. Okay. Since we are doing modulo reparameterization, blah blah, I will only get two elements for the moduli space of flow lines between P and Q. Okay, so now we have a sort of sense of what does this mean. I can talk about the differential map. Goes from MCK, it's a homology theory, so So by definition, differential of a critical point, basically you sum over all points of index, I'll say k minus 1. You take the cardinality of the moduli space of flow lines from MP and Q, and you multiply it by Q. So this is my differential, and critical points, they generate my complex. Okay, I guess I should give an example, hard example at this point. So now we also consider one more time as 2, but this time with the Morse function, f, so that S2 looks like I don't know what to say, a sausage. You have a critical point, saddle point, and a minimum. Okay, so let me denote this by A, and this by B, and this by C, and this by E, because I don't want to confuse with the differential. Okay. We know that A and B, so the critical points of index 2 are only A and B, and of index 1 is C, and of index 0 is E. So let me consider Morse complex or of degree 2. It is just Z2A direct sum Z2B. Okay. Now I have to study the A. So there's only one point, which is C. Basically, I should take the cardinality of the moduli space of flow lines between A and C times C. Okay. So how do I get this moduli space graphically? Basically, I think of flow lines as something moving with gravity along the surface. So I only have one up to parameterization from A. So basically, this will give me, let me denote this by alpha. So I only have one direction. Yeah.
Sorry, I have a question.
Yes, sure.
What does the thing inside the absolute value mean? The Morse AC? MAC?
That's the cardinality of the moduli space of flow lines between A and C.
Oh, okay, okay. Thank you.
Yeah, no worries. Okay, so in this case, it is C, right? Because I only have basically up to reparameterization one way to go to C from A, which is along alpha. Okay. And similarly, if you do the same calculation, dB, it will be C, and you only have basically one way, which is beta. Okay. Now let me talk about MC1 of F. That's actually just C2 with C. Okay. And if I want to talk about the differential, so there's only one point. So I consider the cardinality of this space times E. Now there are two directions that one would like to go from C to E along the gradient, along the vector field given by F. So that's actually 2E, and since we are in Z2 coefficients, that's actually 0. Okay. So from here, one can see that MC0, or no, let me say Okay, we know MC0 is actually just Z2 generated by E. And MC0 of just Z2 generated by E. Okay, so now let me compute then Morse homology. That would be Z2, 0 degree.
Sorry, I'm not.
Yeah.
Sorry, another question. So you can go from A to E following minus the gradient, right?
E from A to what?
E.
Yes. Yes.
Why are we not considering E in the differential of A?
Basically, when I want to compute the differential, I consider the moduli space between 2 points where the index just varies by 1.
Ah, okay.
But what you're saying is actually also used when you want to show that this is actually a differential. That means d squared is 0. And yes, you use this and you prove you actually have a two-cell. But I guess I will not say anything about this at this moment.
Okay, thank you.
You're welcome. Any other clarifications?
I have a question. What
Yes.
does it mean by reparametrization in this case?
Okay, so basically where you parameterize the domain of such a curve. Yes. Yes. So you are actually looking for curves where they are defined on R from minus infinity to infinity, and limit as it tends, for instance, to minus infinity. Okay, let me say about alpha. Okay, the limit as it tends to minus infinity, it would be A, and at plus infinity, it would be C. Milner showed this calculation for actually. I'm sorry, I'm reading the chat. But does it make sense, really?
I think so.
Yeah.
I don't know. At first, I kind of thought that the way I see it is maybe perhaps something related to like isotopy, something, but I don't know.
Yeah. So you discard all of these notion speeds and blah blah. So you just care about in how many directions, sort of.
Sure. All right.
Yeah.
Fair enough.
Okay. I guess there's another topic going on in the chat. Okay. And if you do the computation well with the kernel of the differential in degree 1, so on and so forth, you will get that MH1 is actually 0, and I mean HM1, HM2 is Z mod 2. And so basically, as you can see, you recover the cellular homology of S2. And in fact, let me just state it as a theorem for clarification. So the Morse homology given by a Morse function. Here I'm thinking of it as a graded ring or so. Yes, graded, writing it all degrees, direct sum of degrees. This is actually the same as the singular homology, but with Z2 coefficients. I guess that's it, because otherwise I would end up spending 20 more minutes to talk about more interesting stuff, namely this. So I will leave it like this for now, and would like to answer your questions if you have any.
Yep. Does anyone have any other questions?
Oh, you're welcome.
Maybe just one, we consider Morse function. We also choice of metric, like a manifold, smooth manifold with metric, and so we can define the gradient flow line. The gradient flow, consider what is a smooth structure gradient flow line, and choice of Morse function give us a critical point and gradient flow line connecting them. What is the point of Morse homology or cohomology is Morse homology is topological invariance of smooth manifold. Because does not depend, like a Morse homology, like a Morse complex would be changed, but Morse homology is independent of choice of the Morse function. That is a kind of, we can construct a smooth homotopy between like those things, like that is a Morse theory. And like, for example, interesting is because yesterday was Professor Eliashberg's colloquium talk, like what is the symplectic geometry? Like consider like embedded some manifold of C to the n that is called Stein manifold, like some kind of complex manifold. And it has a symplectic structure, and symplectic area considering Morse theory on Stein manifold that is called Weinstein manifold. It has a symplectic structure, Morse function, and gradient like a vector field, and they construct that combination construct the symplectic structure, like a symplectic Handel decomposition. That gave us symplectic structure. Morse theory gave us smooth structure. And if we consider a symplectic structure, there is a Weinstein Handel body decomposition. There is a symplectic like that.
Yes.
And there is a more stories going on, and that category Morse theory is done by Weinstein and Eliashberg. But the homology level, the important thing is independent of choice of Morse function, independent choice of like definitely yeah, some independence is important to build homology theory.
Yes, 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 true. I was so sloppy, you know, I should have said a word about the homology is independent of our choice of Morse function, but I tried to identify everything with cellular, so I guess it was sort of, yeah, but yeah, thank you.
Any other questions or comments? Well, if not, let's thank the speaker again. Thanks very much. It was a good talk.
Yeah, thank you very much. It was great. Great talk.
Yeah.
And now let's just multiply everything through by 50.
So I'll see you guys next week. All right. So that will be the last talk until before we hit Thanksgiving, basically. Right. Goodbye. Have a good weekend.
Nice talk. See ya.